You're probably wondering why you can't hear them right now. I'll tell you why. It's because of waves. Or should I say, a lack of waves. Let's go ahead and change that, shall we?
So, yeah, I can do the game.
Yeah, me too, I'm going. It's gonna be a great game.
Wait, who are you?
I'm just a simple scientist, but that's not important. What is important is what we've just stumbled upon, and that's waves.
Well, what are waves?
Yeah, what are waves?
So let's talk about that. A wave is a series of periodic disturbances that transfer energy through a particular medium. Here's the kicker though. Waves only transfer energy, no mass. The current definition of a wave is actually quite a bit different than what it used to be considered. Back in 1665, when an Italian priest/physics enthusiast named Grimaldi began studying the diffraction of light, he concluded that light must have been some sort of tiny fluid that was in a constant state of vibration, or a wave. Now, while he was on the right track, he was still a bit off on what a wave actually is. What we know now is that there are actually a few different types of waves. They're defined both by what they vibrate, which is their class, and by what direction they vibrate, which is their shape. First, let's start off with what the classes are. Mechanical waves are waves that vibrate the particles of a physical medium, like air, water, wood, or a ton of other materials. Electromagnetic waves are waves that vibrate electric and magnetic fields, which aren't actually physical mediums. There are also two shapes of waves, a transverse wave and a longitudinal wave. Now first, let's show a transverse wave. This is what a transverse wave's motion looks like. It vibrates a medium perpendicular to the path the energy travels. There are a few key terms to know when looking at a diagram of a transverse wave. The rest position of a medium is known as its equilibrium position. This is the position where the particles of the medium would be if there was no energy running through them. The uppermost point of the wave's path is known as the crest. The lowest point of the wave's path is known as the trough. The point at which a wave in motion passes through its equilibrium position is called a node. This is what a transverse wave looks like in action. Now, this is a longitudinal wave. Its motion is pretty different from a transverse wave. When it vibrates a medium, the vibrations are parallel to the path the energy travels, not perpendicular. There are two main components that you need to know on a longitudinal wave. The first is a compression. This is the point on the longitudinal wave where the medium's particles are most concentrated. The second component that you need to know on a longitudinal wave is called a rarefaction. This is what a longitudinal wave looks like in action. Despite their differences, all waves do have a few particular qualities in common. The first quality is a wavelength. This is represented by the Greek letter lambda in most equations, and this is the distance of one full vibration of a wave. For a transverse wave, this would be from either one crest to the next crest or one trough to the next trough. For a longitudinal wave, this wavelength would actually be from one compression to the next or from one rarefaction to the next. The second quality that all waves have are amplitudes. Now, on a transverse wave, an amplitude is the maximum displacement that a particle makes whenever it's vibrating. This is also known as the distance from the rest position to the crest or the rest position to the trough. Now, again, in a longitudinal wave, it's different. Amplitude is a lot more about the rise and fall of pressure in a particular medium, because longitudinal waves are all about pressure. The third quality that every wave has is called a period, and the period of a wave is the time it takes to make one full vibration. The final component or characteristic that all waves have is its frequency, and the frequency is the number of vibrations a wave makes in 1 second. There are also 4 principles that apply to every single wave, and here they are. The first is that a wave's speed is always constant if it stays in the same medium. It's never going to change if it stays in that same medium. The second principle is actually an inverse relationship. The period of a wave equals the inverse of the frequency, and the frequency of a wave equals the inverse of the period. The third principle in word format says that speed is directly proportional to the wavelength times frequency. This is actually an equation, V equals lambda F. This equation is the foundation for all wave problems. Every equation used in a wave problem is either this very equation or a derivation of it. The final principle that pertains to all waves is this. The faster a wave vibrates, the shorter its wavelength is. Notice that this statement does not talk about the speed of a wave, because we know that, according to the first principle, a wave's speed will always remain constant if it stays in the same medium. So, did you guys learn something?
Yeah, I learned a ton.
Me too, like this. Fun fact, the speed of sound is 767 miles per hour. Fun fact, the scientific study of sound waves is acoustics.
Sweet, I'm glad you guys learned a lot, and I hope you did too.